In our next example, we're given a cubic and a quadratic function, and we're being asked to find the area between these two regions. The area of the region enclosed by these two curves. It's helpful to first start off with a graph of these two functions so we can see which function is on top and which function is on the bottom. And that's also going to help us figure out what our limits of integration will be. So to help us with that, here is a graph of this cubic function and this parabola, and notice that the cubic and the parabola, there are two different regions that are enclosed by the graphs of these functions. So we have a region over here on the left that I'm shading in dark blue, and in that region on the left, the cubic function that's in red is on top. Then we have a region on the right that I'm shading in orange, and in the region on the right, the parabola, the green function, is on top. So there's a few things we have to do. We first have to figure out what are these points of intersection, what are these x values, because we're going to have to split this up into two separate functions. Now for each one of these regions, I am going to draw a representative rectangle. So what I mean by that is for this first region, I'm going to come in and draw a vertical rectangle. It doesn't matter where you place the rectangle, but what's important is that we're seeing in that rectangle that the top of that rectangle is hitting the cubic function and the bottom of that rectangle is hitting the parabola. I'm going to do a similar thing in the second section. I'm going to come in and draw a representative rectangle, and what's important here is that the top of this rectangle is hitting the square function and the bottom of that rectangle is hitting the cubic function. So now let's go look for what our points of intersection are, and we're going to find them by setting these two functions equal to each other and solving the equation for x. I'm going to solve this equation by getting 0 on one side and then factoring this equation. So I'm going to move everything over to the left side of the equation, giving me 3x cubed. My x squareds will cancel when I move it over, and then I'll have a minus 12x is equal to 0. We can factor out a 3x, leaving us with x squared minus 4. And then the x squared minus 4 factors into x plus 2, x minus 2. So now we can see that the x coordinates for our 3 points of intersection, after we set each 3 of these factors equal to 0, are x equals 0, x equals negative 2, and x equals positive 2. So now that we know what the x values are, we're able to set up an integral, or integrals plural, for the area. We are going to need two separate integrals. One for the first region in dark blue. That first region starts at the x value of negative 2. That is this x value here. We don't know what the y value is, and it's not terribly important. And runs up to the x value of 0, up to that region there. And in that region, the cubic function of 3x cubed minus x squared minus 10x is on top. So from that, we will be subtracting the parabola, which is a negative x squared plus 2x. We're integrating that with respect to x. To that integral, we will need to add the area that is in orange that starts at the x value of 0 and goes off to the x value of 2. And in that region, the parabola of negative x squared plus 2x is on top, so we'll put that first in the integral. And from that, we will be subtracting the cubic function of 3x cubed minus x squared minus 10x, and we are integrating this with respect to x. So we have to make sure that we split this integral up, because whichever function is on top needs to be written first on the inside of the integral. So simplifying these integrals, we have the integral from negative 2 to 0 of 3x cubed minus 12x dx, and from that we are adding the integral from 0 to 2 of negative 3x cubed. I'm combining like terms on the inside of my integral. My x squareds will cancel, and I'll be left with a positive 12x dx. I'll go ahead and integrate these using the power rule for integration, leaving me with 3x to the 4th minus 6x squared. That will be evaluated from negative 2 to 0, and to that We will add what we get from the second integral, which will be a negative 3x to the fourth divided by 4, plus 6x squared. That will be evaluated from 0 to 2. When we evaluate the first integral at 0, we get 0. From that, we subtract. Substituting in negative 2 leaves us with 12 minus 24. Moving on to the second integral, we first substitute in our upper limit of 2, which leaves us with negative 12 plus 24. And when we substitute our lower limit of 0, we do not get anything, which leaves us with our final answer of 24.